Hi everyone, it's Ethan Teaches Maths, and today I'm going to carry on looking at the mechanics question from January 2008. It's question 7, and we're going to look at part C today. Alright, so let's get started. So part C really separates the A-star students from the rest. I think this is the hardest bit in A-level maths because it involves actually thinking, which is pretty difficult in this type of example. Okay, so we have B falls a distance of h. It hits the ground and does not rebound. Particle A is then a distance a third of h from P. Find the speed of A as it reaches P. Alright, perfect. So the method that I use to approach these questions is draw some pictures, which I've already got drawn here, and go from there. So looking at the first picture on the left hand side, we can see that A is a third of h from P because B has travelled h meters down from its initial position, which I've just drawn in with this dotted line over here. So you think about that for a second. The fact that B has fallen h meters down to hit the ground, if A starts here, then what's the distance from the starting point to A? Yes, it is again h meters because they're connected by a string. So if B travels down h meters, that means A will travel to the right h meters too. Then the second diagram shows what happens when A reaches P. We want to find the speed when A reaches P. So how do we find the speed at which A reaches P? So what we're going to do is we're going to use Suvat. So I write Suvat in a vertical line downwards just to make it super clear about what's going on. So when you do Suvat, you're doing Suvat from one point to another point. So we're doing it from the point where A is a third of h away from P, and so I'm going to say here, if I call this point O, we're going to go from O to P. So from O to P, A has travelled a third of h meters to the right, so I'm going to resolve towards the right. All that means is I'm telling the examiner that I'm taking all the arrows, everything travelling towards the right as positive. What's its initial velocity when it was at O? We don't know, so I'm just going to write U. V, what's its final velocity when it reaches P? That's literally what the question's asking, so we'll put a question mark there. The acceleration of A from O to P, again, we don't know that, and time, we don't know that, but that's irrelevant for this question. So we need to find some unknowns, V, U, and A. 3 unknowns in one Suvat equation. Obviously, that's impossible, so we're going to have to find U and A separately. So how do we find the initial velocity? The velocity of A when it's at this point here on the left hand side. How do we find that initial velocity? Well, we do it by writing out, of course, another Suvat equation. So again, I said Suvat is always from one point to another point. So let's call this point here O prime. From O prime to A, we want to find the velocity when it reaches A. So it will have velocity U at O prime, it will have velocity V at A. The distance it's travelled to go from O to A is h. Initial velocity is 0. Final velocity, I said that's what we want to try and work out. A, so what's the acceleration? Well, in the previous part of the question, we saw that acceleration, because they're connected by a light inextensible string, is 4/9g, and time, we don't care. I'm not writing units in, it's a bit irrelevant for this question, because it's SI, standard index units, SI units, it's just implicit. Okay, so what Suvat equation doesn't include t? Well, it's v squared equals u squared plus 2as. This is going to give us very quickly 0 plus 2 times A times S. So no, V squared is 8 over 9 GH. So V is equal to the square root of 8 over 9 GH. Okay, then just to make it crystal clear, what I'm going to do, I'm going to highlight this V in yellow, and we're going to put that value of V as our initial velocity in the second diagram. Okay, so I'm going to do the next part in a different color, in blue. What am I going to do in blue? In blue, I'm going to find the new acceleration of A. Okay, firstly, why do we need to find the new acceleration of A? Well, because B has hit the ground, the tension in the string has disappeared. Because when B hits the ground, implicitly the string becomes slack. That means there is no more tension in the string. Because there is no more tension in the string, that means there is nothing pulling A along towards the right. There is no driving force for A. Because there is no driving force for A, the only forces acting on A, if I'm going to draw this out again, so we have the particle A, there is no driving force, there is no tension. All there is friction. And there's friction because it's on a surface, a rough surface, so friction will act to slow it down. Eventually it will stop. But in this case, it's going to hit the pulley P. So what is the new acceleration? Well, we're going to use F equals ma. So we're going to resolve to the right. We're going to use F equals ma. What are the forces acting towards the right? There are none. What are the forces acting towards the left? Mu r. Now we were told in part B that mu is 2/3 and r, well, how do you work out what r is? To work out r, we resolve upwards. We have to look at the forces, what one's going upwards. Here we know it's r going upwards, mg going downwards, so that's negative. What's the acceleration? Well, 0, because it's not floating off of the ground. It's not magically levitating from the ground. So acceleration 0. So it's just equal to mg, and that's equal to ma. M, because the mass of A is m. Now we can cross out the m's, and that means the acceleration is going to be 2/3 of g. Now I've done something on purpose. I left something out. Can you see what I left out? I left out a minus sign. Why didn't I write that in? I wanted to see if you would check it. There's a minus sign there because it's acting towards the left. That means because we're resolving towards the right, everything acting towards the left is negative. Therefore, the acceleration is negative. Now, what do we call a negative acceleration? We call a negative acceleration deceleration. Why do we call it deceleration? Because it's the opposite of acceleration. It's slowing down. Okay, cool. And it's going to slow down. So we expect the velocity at p to be less than this, the square root of 8 over 9 gh. So what we're going to do with this new acceleration? Well, we're going to get this new acceleration, which is minus 2/3 of g, and we're going to stick it into here. We're going to stick it into our original equation from O to P. So now we're done. So we have v squared equals u squared plus 2as. V squared we're trying to work out. U is 8 over 9 gh, that's u squared, minus 2 times a, which is 2/3 of g. I put a minus here because 2/3 g is negative, and then s is 1/3 of h. Okay, and then do some maths. So we're going to do some basic algebra, simplify this equation. that's minus 4 over 9 GH. We're going to take away these fractions. They have a common denominator of 9. So that's 4 over 9 GH. And then square root both sides. And you get 2/3 square root GH. And that's it. Hopefully that was really clear. And if it wasn't, leave a question in the comments below. And I'll be happy to get back to you. 9 out of 10 times, this is the method that you use. I always write out the pictures first, so what's happening, and then I'm filling the blanks. We need to find U, we need to find A, so that's what we do. Okay, brilliant. I'll see you in the next video.